Now you might have been asking yourself, what is the application? Why do we care if the magnetic field has a force on a wire? Well, on an individual wire that doesn't have a whole lot of use, but it does have an immense amount of use when we talk about making that wire into a loop, because this is how all motors and generators work. Motors and generators are basically the same thing, just what's being converted into what. For a generator, mechanical energy is being converted into electrical energy, and for a motor, electrical energy is being converted into mechanical energy. So here we'll find that the net force is 0, but the net torque is not, meaning that it will sit, but it will spin. So what happens is that we have that BIAN, so that Bill force, but now instead of an L, we have the area. So the L turned into an area of our loop, and here the N represents the number of loops that we have, because as we add more and more loops to the motor or generator, the stronger and stronger the force will be. So this applies to any shaped loop. We are going to draw these typically as nice squares, but they can be circles. And when I show you the actual motors, you find that they're not really either of those shapes, they're just round. N is the number of turns. The torque has a maximum value when we're equal to 90 degrees, when basically this has turned such that the magnetic field is going directly through the area, not when it's horizontal. The torque is 0 when the field is parallel to the plane of the loop. So when our plane is just straight across, the torque is 0, because basically the forces balance out exactly. Well, we'll look at that in more detail. So another quantity to be aware of, we're not going to use it a whole lot, is what's called a magnetic moment. You probably have heard this magnetic moment idea in chemistry class, and we'll talk about this more when we get into atomic structure. But this is a magnetic moment, very similar to what we think of as an electron. Why some electrons are said to be up or down, or has a positive or a negative magnetic spin value. What the magnetic moment is for a loop is a vector pointing in the same direction as the area vector, so it's perpendicular to the plane of the loop. It's given the symbol mu, and basically is the quantities that we can control. The amount of current going through the loop, the area of the loop, and the number of n in the loop. And so the equation can be shortened to that the mu is all the things that have to do with the loop itself and the external magnetic field. So the bigger a magnetic moment for our loop, the more torque we have on our loop. Okay, so what is a motor or a generator? Well, we just said it was a thing that converts between electrical and mechanical energy. So it needs something that has electricity running through it and something that turns. So here we have the very, very simplest diagram of a motor, where we have a loop that is in a magnetic field. And this magnetic field can either be a permanent magnet or an electromagnet. We'll talk about how to make an electromagnet mostly next time. But basically there are two types of motors. You have a brushless motor and one with brushes. So I'll have motors in class that we can take apart, but here you can see the windings. It's not the nice square that you see on the picture. And you have the magnet. This one, the magnet is in the center, which you don't need brushes, because brushes are used to get the electricity from the stationary outside world to the spinning inside world of most motors. This one happens to be a brushless one because it's the magnet that spins. Then we also have motors that are the other way, and this motor would have brushes. I don't know where the brushes went, but you can see the windings in here. They're not the nice square, but they're just wound up, and I'll pass these around in class. And then on the inside of here you have a magnet. You can tell that because when I get this thing close, it wants to stick. So if I get it shoved in there right, but the thing turns on the inside. And so you can kind of see it turning on the inside, that those are the coils turning on the inside of the magnet. So that's exactly what we see here in this diagram of the motor. Is we have the communicator that communicates the current from the outside world to the inside world of the spinning, and that's done with brushes. Instead of having an actual plug-in, we need a connection that can move, and that's basically brushes. It looks like a little broom. And then the shaft on the inside, the windings or just wound copper, not a particular shape, and certainly not the square loop that we have here. But basically the idea is that the motor has a magnetic field that a loop is turning that has current going through it. So the torque acting the loop will tend to rotate the loop to smaller values of theta until it becomes 0. But here we have the same problem as we do with a pendulum, is that it overshoots. So even though the torque at that very instant is 0, the motor is rotating and will tend to rotate through that, have a higher force, and keep going. So we have to basically get the motor started, which can easily be done with the electricity. Then we have two types of motors and generators. You have AC motors, which means alternating current, and DC motors. And basically, all you have to do is change this component of the communicator in order to change it from an AC motor to a DC motor. So actual motors contain many, many loops instead of just the one. We just have the one here pictured, so you can hopefully get an idea of what happens in the magnetic field. But as you saw, a real motor has lots and lots of loops in it. So thousands and thousands in order to create the amount of torque that we desire to run your car, run a screwdriver, run all this equipment. Okay, so now let's do a problem where we have a loop of known area that we want to figure out the forces and the torques on it. First thing we want to do is use our right-hand rule to figure out what is going on this particular loop. And so here we have our magnetic field is B. So we would be pointing our hands to the left to go with that magnetic field. And then we're going to point our thumb in the direction of each one of these. So on the left side there, we have the magnetic field moving to the left and our thumb moving up. And so we would smack ourselves in the face. So the force is out towards us. So we would write that as a point because the force is out towards us. Then as we follow our current around, keeping the magnetic field going this way, we can't turn our magnetic field because it goes that way, but we turn our thumb to point the other way. I can't really do that, but the angle between them is 0 or 180, and so the force on the top is 0. And then we move to the other side where we have the current going down, so the thumb's going down, the magnetic field is still going to the left, so the force is going to be into the page. So we write that as an arrow and going away from us. So this is out and this is into the page. And then we bring our hand down and now our current is going the same direction as our magnetic field, and so the angle is 0 because it's moving, the B is moving to the left, the velocity of the current is moving to the left, and so the force on the bottom is 0, exactly 0. So now we can calculate the two non-zero forces on this particular loop. So we can do this one of two ways. The forces are going to be equal to BIL, and the torque we said is equal to BIAN. So we're going to use both equations basically to prove that they're the same equation when you take into account that the one is a torque. So the force is BIL on each wire, so we'll calculate the force on the left wire first. They're going to be the same, just opposite directions. So it said it was 2.5 Tesla, that's right there. And the current is 1 amp, that's current. And then we have a length, so 20 centimeter by 30 centimeter. It looks like that side's shorter, so we're going to say that's the 20 centimeter side and this is the 30 centimeter side. So we get 20.2 meters and sine of 90 degrees. Because we're either 90 degrees or 270, so we're either going to be positive or negative. So it's 0.05 newtons. So that's the force in or out of the page. And then we want to find the torque. We can do that two ways. Torque is equal to BIAN, sine of theta. And so we're going to use the same numbers we did before, times the current, times the area is now the 0.2 by 0.3, and times n. There's just one loop here, so we're just going to put 1 in there, and sine of 90 degrees, and we get 0.15 Newton meters. The other way to calculate torque is force times a distance. And so if it's going to spin around the center, that side is 30, then this is 0.15 meters this way, and 0.15 meters this way. So we get our force, 0.5 newtons, times, and there's going to be 2 forces, 1 on each side, so times 2, and then times 0.15 meters, and that gives us 0.15 newtons per meter, because we had a 1/2 here times a 2 times 0.15 gives us 0.15 Newton meters. So we get the same answer either way we calculate force, because we have basically on the torque, we have 1 torque coming out and we have 1 torque going in, which is why we have 2 forces coming onto this loop. Now your challenge question is, what is the net force on the loop? So think about it for a minute. We figured out what the number was. Find out what the net is. And again, the net is the sum of forces. F net is equal to your sum of forces. So think about it for a minute. Okay, hopefully you figured this out, that we have basically 0.5 newtons out of the page and 0.5 newtons into the page. So that's, we're going to call this one positive and we're going to call this one negative. So if I have plus 5.5 newtons and minus 0.5 newtons, we end up with a net force of 0 newtons. So this thing won't go anywhere, but it will spin around. And here are all those values again